In the beginning, there was darkness. Then, from the cold depths of interstellar space, a shock wave rippled through a giant molecular cloud, and everything changed. What followed was the most extraordinary transformation in cosmic history. A 4.5 billion-year journey from swirling dust to living worlds, from chaos to the emergence of consciousness itself. This is the complete, untold story of our solar system's birth, death, and resurrection across deep time. The Cosmic Awakening, 4.6 to 4.5 billion years ago. Somewhere in the Orion arm of the Milky Way galaxy, a massive star reached the end of its violent life. In a cataclysmic explosion that outshone entire galaxies, this ancient giant hurled its enriched elements across light years of space, sending shock waves racing through the cosmic void. The supernova's death cry would become our solar system's birth announcement. The shock wave struck a seemingly unremarkable molecular cloud, a frigid, dark nebula stretching several light-years across and containing the mass of 1,000 suns. For eons, this cloud had drifted silently through space, its temperature hovering just 10 degrees above absolute zero. Hydrogen molecules moved sluggishly through the darkness, occasionally colliding in the near-perfect vacuum. But now, compressed by the supernova's expanding shell of stellar debris, gravity began to win its ancient battle against the outward pressure of gas. What happened next defied every human sense of scale and time. The cloud began to collapse under its own weight, slowly at first, then with gathering momentum that would reshape the fabric of spacetime itself. As the nebula contracted, it began to spin faster, obeying the same physical law that makes a figure skater accelerate when pulling in their arms. The conservation of angular momentum transformed a roughly spherical cloud into a flattening disk, with most of the material spiraling inexorably toward the center. At the heart of this cosmic maelstrom, temperatures began to rise. The gravitational energy of countless particles falling inward converted to heat, warming the nebula's core from the bitter cold of interstellar space to hundreds, then thousands of degrees. When the central temperature reached 10 million degrees Celsius, hydrogen nuclei began fusing into helium, and our sun ignited. The violent birth of this new star sent shock waves rippling outward through the surrounding disk, marking the true beginning of our solar system's story. But this solar nebula, as astronomers call the disk of gas and dust surrounding the young sun, would not endure. Recent research by MIT scientists using paleomagnetic analysis of Ongrite meteorites reveals that this primordial disk persisted for only 3 to 4 million years, a cosmic heartbeat in which all the building blocks of planets had to form. During this impossibly brief window, 99.5% of the nebula's material collapsed into the sun, while the remaining 0.5% spread into a thin disk extending outward for hundreds of astronomical units. The disk was not uniform. Temperature gradients proved crucial for everything that followed. In the innermost regions, within about 0.7 astronomical units of the sun, temperatures soared above 1,500 degrees Celsius, hot enough to vaporize rock itself. Moving outward, the disk cooled dramatically. At Earth's current distance, temperatures dropped to around 300 degrees. But it was at 2.7 astronomical units from the sun, roughly where the asteroid belt now lies, that the most significant boundary formed. Scientists call this the frost line, and it would determine the fundamental architecture of our solar system. Beyond this invisible barrier, temperatures fell below the freezing point of water, allowing ice crystals to condense from the nebular gas. This seemingly simple phase transition had profound consequences. In the inner solar system, only rocky and metallic materials could remain solid, comprising less than 1% of the available matter. Beyond the frost line, the addition of water ice increased the solid material by a factor of 3 to 4, providing enough building material for massive worlds. The supernova that triggered our solar system's birth also delivered a deadly gift. Among the elements hurled across space were short-lived radioactive isotopes, particularly aluminum-26 with a half-life of just 720,000 years. These unstable atoms would act like tiny furnaces, heating the earliest solid materials to form in the solar nebula. Evidence for this primordial radioactive heating comes from meteorites containing distinctive mineral assemblages that could only form under specific temperature conditions. Within the first million years, the disk began developing structure. Computer simulations reveal how density waves propagating through the nebula created rings and gaps, while magnetic fields channeled material along complex trajectories. Turbulence generated by the magnetorotational instability stirred the disk. Mixing materials formed at different temperatures and distances from the Sun. This early mixing explains why meteorites contain both high-temperature minerals that formed near the Sun and ice crystals that condensed in the outer reaches. The young Sun itself played a crucial role in sculpting the disk. Unlike the stable star we know today, the early Sun was a violent, erratic variable star. T-Tauri winds, powerful stellar gales, blew outward at speeds of hundreds of kilometers per second, gradually dispersing the remaining gas from the inner solar system. These winds carved away the lighter elements, leaving behind only the rocky and metallic materials that would eventually coalesce into the terrestrial planets. But perhaps the most remarkable aspect of this cosmic awakening was how quickly solid materials began forming. Within just thousands of years of the Sun's ignition, the first solid particles condensed from nebular vapor. These calcium-aluminum inclusions, preserved today in primitive meteorites, formed at temperatures exceeding 1,300 degrees Celsius and represent the oldest dated materials in the solar system at 4.568 billion years. The condensation sequence followed predictable patterns based on temperature and pressure. Closest to the Sun, refractory elements like titanium, aluminum, and calcium combined to form the first solid grains. Moving outward, iron and nickel condensed into metallic particles. Beyond the frost line, water ice joined with rocky materials, while in the outermost reaches, even more volatile compounds like methane and ammonia could freeze. These microscopic grains would not remain isolated for long. Electrostatic forces caused them to stick together when they collided, forming fluffy aggregates that grew larger through continued accretion. Turbulence in the disk helped concentrate these particles into dense clumps, while gas drag caused them to spiral slowly inward toward the midplane of the disk. Within perhaps 100,000 years, a remarkable transformation occurred. The countless tiny grains had grown into objects kilometers in size, the first planetesimals. These rocky and icy bodies, ranging from mountain size to larger than modern asteroids, represented the fundamental building blocks from which all planets would eventually form. The solar nebula's brief existence set the stage for everything that followed. The temperature gradients established during these first few million years would determine why Mercury, Venus, Earth, and Mars became small, rocky worlds, while Jupiter, Saturn, Uranus, and Neptune grew into gas and ice giants. The timing of disk dispersal explained why the inner planets remained relatively small. By the time their solid cores could capture significant atmospheres, the solar winds had already blown most of the gas away. As the nebular disk finally dissipated, blown away by the young Sun's increasingly powerful stellar winds, it left behind a collection of planetesimals orbiting in the darkness. The cosmic awakening was complete. Now began the longer, more violent process of planetary assembly. A story of catastrophic collisions, chemical evolution, and the gradual emergence of worlds that would one day harbor the complexity of life itself. The stage was set for the next chapter, the transformation of dust into worlds. 2. Dust to worlds. 4.5 to 4.4 billion years ago, the cosmic awakening had ended, but across the darkened disk, a more subtle transformation was beginning. In the silence left by the dissipated solar nebula, countless planetesimals drifted in solitary orbits, each one a mountain-sized fragment of the original cloud. Yet within this apparent stillness, forces older than the solar system itself were stirring. Gravity, that most patient and inexorable of cosmic architects, began the slow work of building worlds. What happened next would have seemed impossible to any observer. Tiny grains of dust, each smaller than a mote floating in sunlight, somehow grew into objects the size of planets. The journey from microscopic particles to massive worlds required a precise choreography of physical processes, each step building upon the last in an ascending spiral of complexity that defied the random chaos of space. The process began with the most fundamental force in nature, the simple attraction between particles. In the cold vacuum of the early solar system, dust grains moved at relative speeds of just meters per second, gentle enough that when they collided, van der Waals forces and electrostatic attraction could make them stick. These weak molecular forces, the same ones that allow a gecko to walk on glass, proved strong enough to bind cosmic dust into ever larger aggregates. Within perhaps 10,000 years, fluffy clusters of particles had grown to centimeter size. These fragile assemblages looked more like soot than the solid building blocks of planets. Yet they possessed a crucial advantage. Their low density allowed them to sweep up additional material with remarkable efficiency. Like cosmic snowballs rolling through a field of dust, they gathered mass with each orbit around the young sun. But growth could not continue through gentle collisions alone. As objects reached meter size, their increased mass and gravitational pull began accelerating collision velocities. Many impacts became destructive rather than constructive, shattering the delicate aggregates back into their constituent pieces. For planetary formation to proceed, some mechanism had to overcome this collision barrier, what scientists call the meter-size problem. The solution came from the disk's own turbulent nature. Even after the solar nebula's gas had largely dissipated, residual turbulence created local concentrations of solid particles. In these dense regions, gravitational instabilities could trigger rapid collapse, bypassing the destructive collision phase entirely. Within perhaps a single orbit around the Sun, diffuse particle clouds collapsed directly into kilometer-sized planetesimals, the first true solid bodies in the solar system. These primordial planetesimals, ranging from 1 to several hundred kilometers in diameter, represented a revolutionary transition in cosmic evolution. No longer subject to gas drag or the whims of turbulent eddies, they followed stable Keplerian orbits determined purely by the Sun's gravity. More importantly, they had crossed the threshold where their own gravitational fields became significant. The era of planetary accretion had begun. The early solar system now resembled a vast shooting gallery, with countless rocky and icy bodies pursuing intersecting orbits through the disk. Collisions between planetesimals followed the ruthless logic of celestial mechanics. Larger objects grew faster than smaller ones, their stronger gravitational fields sweeping up material across wider areas. This runaway growth created a hierarchy of objects, with the most massive planetesimals cannibalizing their smaller neighbors at an accelerating pace. Within perhaps 1 million years, this process had produced several hundred lunar to Mars-sized objects called planetary embryos. Each embryo dominated a feeding zone roughly 10 times its Hill sphere radius, the distance within which its gravity could capture passing material. In the inner solar system, where solid material was scarce, these feeding zones were relatively small. Beyond the frost line, where ice increased the available building material by 3 to 4 times, embryos could grow much larger. Yet the fundamental architecture of the solar system had already been determined by the temperature gradients established during the nebular phase. In the scorching inner regions, only the most refractory materials survived: iron, magnesium silicates, and aluminum oxides. These heat-resistant compounds comprised less than 1% of the original nebular material, severely limiting the size that inner planets could achieve. The frost line at 2.7 astronomical units marked the Great Divide in planetary formation. Beyond this boundary, water ice condensed from the remaining gas, tripling the amount of solid material available for planet building. This abundance of building blocks enabled the formation of massive cores capable of capturing substantial atmospheres directly from the surrounding disk. In the inner solar system, for embryos emerged as dominant, the predecessors of Mercury, Venus, Earth, and Mars. These worlds assembled through a series of increasingly violent collisions as the largest objects in each orbital zone merged with their neighbors. Computer simulations reveal that the final assembly of terrestrial planets required roughly 100 million years of chaotic impacts, with each major collision potentially resurfacing entire hemispheres. The process was far from gentle. When embryos comparable in size to Mars collided, the energy released exceeded the gravitational binding energy of both objects combined. These hypervelocity impacts generated temperatures exceeding 6,000 degrees Celsius, hot enough to vaporize rock and create global magma oceans hundreds of kilometers deep. The early terrestrial planets existed as molten, hellish worlds bearing no resemblance to the cool, stable bodies we know today. Each collision brought dramatic consequences. Massive impacts could strip away existing atmospheres entirely, while simultaneously delivering new volatile materials. The angular momentum imparted by off-center collisions determined planetary rotation rates and axial tilts. Some impacts were so violent they ejected material back into space, creating debris disks that would later coalesce into moons. The timing of these collisions proved crucial for each world's ultimate fate. Mercury, closest to the Sun, experienced the most energetic impacts in the disk's hottest region. A collision with another planetary embryo may have stripped away most of its rocky mantle, leaving behind the disproportionately large iron core we observe today. Venus assembled more gradually, retaining a thick mantle and developing the slow, retrograde rotation that characterizes it still. Earth's formation story centers on one of the most significant events in solar system history, the collision that created our moon. Approximately 50 million years after planetary formation began, a Mars-sized impactor called Theia struck the proto-Earth at an oblique angle. The impact's violence vaporized both objects, creating a massive debris disk around Earth that would later condense into our unusually large satellite. Mars tells perhaps the most poignant story of terrestrial planet formation. Located near the outer edge of the terrestrial zone, it should have grown to rival Earth in size. Instead, Mars reached only 11% of Earth's mass, a cosmic accident that may have preserved its potential for past habitability while ensuring its ultimate failure to retain a thick atmosphere and magnetic field. The outer regions beyond the frost line witnessed the formation of entirely different types of worlds. Here, planetary embryos could grow massive enough to capture hydrogen and helium directly from the solar nebula. Jupiter, the first to reach this critical mass threshold, may have formed within just 10 million years, fast enough to capture an atmosphere comprising 90% of its total mass. Yet even Jupiter's formation remained incomplete when the solar nebula finally dispersed. The giant planet's core, revealed by NASA's Juno mission to be fuzzy rather than compact, suggests that core accretion continued even after atmospheric capture began. This discovery has revolutionized our understanding of how gas giants form, revealing a more gradual and complex process than previously imagined. By 4.4 billion years ago, the age of planetesimal accretion was ending. The solar system had been transformed from a smooth disk of dust and gas into a collection of distinct worlds, each shaped by the violent circumstances of its birth. Yet this was only the beginning of their stories. The massive bodies now orbiting the Sun would continue evolving for billions of years, their surfaces sculpted by impacts, volcanism, and the gradual cooling of their molten interiors. The dust had become worlds. Now began the longer journey toward the emergence of life itself. 3. The Giant Impact Era. 4.5 to 4.0 billion years ago, the dust had become worlds, but the violence was far from over. If anything, the solar system had entered its most catastrophic phase, an epoch when planets themselves became projectiles, when entire worlds could be shattered and reformed in single apocalyptic collisions. The newly formed terrestrial planets, still glowing from the heat of their accretion, orbited through a cosmic shooting gallery where mountain-sized asteroids were merely the smallest ammunition. This was the Giant Impact Era, a time when the fundamental architecture of the inner solar system would be decided not by gentle gravitational nudges, but by collisions so violent they defied comprehension. Each impact released energy equivalent to billions of nuclear weapons, sufficient to melt continents and boil away oceans. Yet from this cosmic carnage would emerge some of the solar system's most distinctive features, including the very moon that lights our night sky. The stage for these titanic collisions had been set during the final phases of planetary accretion. As the larger planetary embryos swept up most available material in their orbital zones, fewer but increasingly massive objects remained. These surviving bodies, some approaching the size of Mars, moved in eccentric, intersecting orbits that made catastrophic encounters inevitable. Computer simulations reveal that the terrestrial planets underwent dozens of major impacts during this period, each capable of fundamentally altering a world's character. The most famous of these cosmic catastrophes occurred approximately 4.51 billion years ago, when a Mars-sized object astronomers call Theia struck the proto-Earth in an oblique collision that ranks among the most consequential events in planetary history. The impactor approached from an angle of roughly 45 degrees, traveling at a velocity of 4 kilometers per second, fast enough to circle Earth in just 3 hours. The collision's violence exceeded every terrestrial comparison. Within minutes, both worlds had been reduced to a mass of superheated vapor and molten rock expanding into space. Temperatures at the impact site reached 8,000 degrees Celsius, hotter than the sun's surface, while shock waves propagated through both bodies at velocities exceeding the speed of sound in rock. The impact delivered enough energy to vaporize Earth's entire outer shell and eject massive amounts of material into orbit. What happened next defied the destructive nature of the collision itself. Instead of simply obliterating both worlds, the impact created something entirely new. The debris ejected into space, a mixture of material from both Earth and Theia, began condensing in a disk around the newly reformed planet. Within perhaps 1,000 years, this debris had coalesced into a molten moon, initially orbiting just 20,000 kilometers above Earth's surface. Evidence for this lunar origin story comes from multiple sources that continue to astound planetary scientists. Moon rocks returned by the Apollo missions show an identical oxygen isotope signature to Earth's mantle, a chemical fingerprint so precise it could only result from both bodies forming from the same material. The moon's unusually large size relative to Earth, its lack of a substantial iron core, and its distinctive orbital characteristics all support the giant impact hypothesis. The collision's aftermath transformed Earth into an alien world bearing no resemblance to the blue marble of today. A global magma ocean, hundreds of kilometers deep, covered the planet's surface. The young moon, glowing red-hot from its own formation heat, appeared 15 times larger in the sky than today, raising massive tides in the molten rock below. Earth's rotation period had been accelerated to just 5 hours, while the moon completed an orbit in merely 20 days. Yet the Theia impact was merely one event in a sustained bombardment that pummeled the inner solar system for hundreds of millions of years. The Late Heavy Bombardment, spanning from approximately 4.1 to 3.8 billion years ago, represents the final phase of planetary formation, a cosmic cleanup operation that determined the ultimate fate of every terrestrial world. This prolonged assault originated from the outer solar system, where the giant planets were still migrating to their final positions. Gravitational interactions between Jupiter, Saturn, Uranus, and Neptune scattered countless planetesimals inward, creating a sustained barrage of impacts on the inner planets. The intensity was staggering. Impact rates were perhaps 500 times higher than today, with objects the size of large asteroids striking planetary surfaces every few thousand years. Evidence for this ancient bombardment is written in the scarred faces of worlds across the solar system. The moon's heavily cratered highlands preserve a record of impacts from this era, with radiometric dating of Apollo samples revealing a clustering of impact melt ages around 3.9 billion years ago. Mars bears similar scars in its ancient southern highlands, while Mercury's entire surface tells a story of relentless bombardment. But the Late Heavy Bombardment was not merely destructive. It also delivered the building blocks of life itself. Many of the impacting objects were carbonaceous asteroids and comets rich in organic compounds and water. These cosmic deliveries may have provided Earth with a significant fraction of its oceans and the chemical precursors necessary for biological evolution. The bombardment's effects varied dramatically from world to world, setting each planet on its unique evolutionary path. Earth, protected by its substantial mass and magnetic field, retained most of its atmosphere and water despite repeated impacts. Mars, smaller and more vulnerable, suffered catastrophic atmospheric loss that would eventually transform it from a potentially habitable world into the frozen desert we see today. Venus experienced its own transformation during this era, though its thick atmosphere and hellish surface have obscured most evidence of ancient impacts. The planet's unusual slow, retrograde rotation may result from a massive collision that literally knocked it sideways, fundamentally altering its spin. Some scientists speculate that Venus may have been habitable during its early history, only to lose this potential as the bombardment triggered a runaway greenhouse effect. Mercury suffered perhaps the most severe battering of any terrestrial planet. One impact was so massive it created the enormous Caloris Basin, nearly 1,500 kilometers across, while shock waves from the collision created strange, hilly terrain on the planet's opposite side. The cumulative effect of countless impacts may have stripped away much of Mercury's original rocky mantle, leaving behind the disproportionately large iron core that gives the planet its unusually high density. Throughout this violent epoch, the giant planets themselves continued evolving in ways that would reshape the entire solar system. Jupiter's gravitational influence prevented the formation of a planet in what is now the asteroid belt, instead stirring the region into a chaotic zone of colliding planetesimals. Many of these objects were scattered into comet-like orbits, becoming the ammunition for the late heavy bombardment. The bombardment also played a crucial role in establishing the volatile inventories of the terrestrial planets. Each major impact could strip away existing atmospheres while simultaneously delivering new materials. The net effect depended on a delicate balance between loss and gain, with larger planets generally faring better due to their stronger gravitational fields. As the bombardment gradually waned around 3.8 billion years ago, the solar system finally began to resemble its modern configuration. Impact rates declined to near their current levels, allowing planetary surfaces to cool and solidify. Atmospheres could accumulate without being immediately stripped away by the next massive collision. Most importantly, conditions became stable enough for liquid water to persist on planetary surfaces, setting the stage for the emergence of life. Yet the scars of this violent era remain visible today. Every crater on the Moon speaks to the chaos of these early times, while the very existence of our satellite serves as a constant reminder of the cosmic accident that created it. The giant impact era had ended, but its legacy would shape the evolution of life itself. The molten worlds were finally ready to cool, to develop stable surfaces, and to begin the long journey toward habitability. For hell and high water, 4.0 to 3.8 billion years ago, the molten worlds were finally ready to cool, to develop stable surfaces, and to begin the long journey toward habitability. Yet as Earth emerged from the chaos of the giant impact era, it entered what scientists have long called the Hadean, named for Hades, the ancient Greek underworld, conjuring images of a hellish planet wreathed in lava and poison gases. For decades, this vision of early Earth as an uninhabitable inferno dominated scientific thinking. But hidden within microscopic crystals no larger than a grain of sand lay evidence that would completely overturn this hellish narrative. The revolution began in the remote Jack Hills of Western Australia, where geologists discovered zircon crystals of extraordinary antiquity. These nearly indestructible minerals, forged in the planet's earliest magma chambers, preserved chemical signatures from a time when Earth was supposedly too hot for liquid water to exist. Yet when UCLA's T. Mark Harrison and his team subjected these ancient crystals to isotopic analysis, they uncovered one of the most shocking discoveries in planetary science. The zircons told a story that defied every expectation. Some crystals dated to 4.374 billion years ago, just 200 million years after Earth's formation. Yet they showed clear evidence of having crystallized in the presence of liquid water. Their oxygen isotope ratios, elevated far above what would be expected from a dry, molten world, could only be explained by interaction with liquid water during their formation. The implications were staggering. Instead of a hellish wasteland, early Earth may have harbored vast oceans almost from the moment of its birth. These microscopic time capsules revealed crystallization temperatures of just 680 degrees Celsius, remarkably cool for a supposedly molten planet. The zircons had formed in granitic magmas that required the presence of water to melt at such relatively low temperatures. Even more remarkably, the crystals showed evidence of multiple episodes of melting and recrystallization, suggesting that water-rock interactions were not just present, but actively reshaping the planet's crust within its first few 100 million years. The transformation from cosmic collision zone to water world happened with breathtaking speed. As the last major impacts of the late heavy bombardment subsided, Earth's surface began cooling from the outside in. The planet's early atmosphere, thick with water vapor from countless comet impacts and volcanic outgassing, reached a critical threshold where steam could finally condense into liquid droplets. For perhaps tens of thousands of years, torrential rains fell continuously across the planet's surface, filling the deepest impact basins and volcanic calderas with the first primitive oceans. But where did all this water originate? The answer lies in multiple cosmic delivery systems that operated during Earth's violent infancy. The primary source was the planet itself, Water vapor trapped within the original planetesimals that built Earth was gradually released through volcanic outgassing as the planet's interior heated and differentiated. Every volcanic eruption, every lava flow, contributed moisture to the thickening atmosphere. Asteroids provided a crucial secondary source. Unlike the popular image of comets as cosmic snowballs delivering Earth's oceans, recent analysis suggests that carbonaceous chondrite asteroids contributed up to 30% of our planet's water inventory. These rocky bodies, formed beyond the frost line but scattered inward during planetary migration, possessed deuterium to hydrogen ratios closely matching modern seawater, a chemical fingerprint that definitively links them to Earth's oceans. Comets, despite their dramatic appearance and water-rich composition, played a surprisingly minor role. Their deuterium signatures are roughly twice that of Earth's oceans, indicating that while cometary impacts certainly occurred, they contributed relatively little to the total water budget. The recent OSIRIS-REx and Hayabusa 2 missions, which found substantial water content in asteroids previously thought to be dry, have further supported the asteroid delivery model. By 3.8 billion years ago, definitive evidence emerges for extensive liquid water oceans. In the Isua supercrustal belt of Greenland, among the world's oldest surviving rocks, geologists have discovered banded iron formations that could only have precipitated from seawater. These alternating layers of iron oxide and chert tell a story of chemical cycling between ocean and atmosphere, of dissolved iron reacting with the first traces of oxygen to create distinctive striped patterns that would become one of Earth's most recognizable rock types. Even more compelling evidence comes from pillow basalts found in the same ancient rock formations. These bulbous, pillow-shaped structures form only when lava erupts underwater, providing direct proof that substantial bodies of liquid water covered Earth's surface 3.8 billion years ago. The discovery of these submarine volcanic formations in rocks of such extraordinary age represents one of geology's most profound revelations about early Earth conditions. Yet this was not the tranquil blue world we know today. The early Earth operated under physical conditions unlike anything in the planet's subsequent history. Heat flow from the interior reached 3 times modern levels, driven by the radioactive decay of short-lived isotopes, residual heat from planetary accretion, and continued bombardment by asteroid impacts. This immense heat flux powered volcanic activity on a scale that dwarfed anything in recorded history. The volcanism of the Hadean and early Archean was dominated by komatiites, ultramafic lavas with magnesium oxide contents exceeding 18% and eruption temperatures reaching 1,600 degrees Celsius. These extreme volcanic rocks, absent from Earth since the Proterozoic Eon, required mantle temperatures at least 300 degrees hotter than today. The komatiite flows created vast underwater lava fields, while their distinctive spinifex textures, formed by rapidly cooling olivine crystals, preserve a record of the planet's superheated early state. Continental crust formation during this era required processes that operated under conditions far more extreme than any modern analog. The creation of the first stable landmasses involved deep melting at pressures exceeding 1.4 gigapascals, equivalent to depths of 50 kilometers or more. This suggests that some form of subduction-like process was already operating, cycling oceanic crust back into the mantle and generating the first granitic rocks through hydrous melting. The distinctive TTG suite, tonalite, trondhjemite, and granodiorite compositions that dominate Archean cratons provides crucial evidence for early water cycling through the mantle. These rock types require hydrous melting conditions with approximately 2% water content by weight, indicating that water was not just present at the surface but actively participating in deep crustal processes. The formation of TTG magmas represents one of the earliest examples of the water cycle operating on a planetary scale. Throughout this era, the interplay between water and rock was reshaping Earth's surface at unprecedented rates. Chemical weathering proceeded rapidly in the hot, humid conditions, breaking down volcanic rocks and delivering dissolved minerals to the growing oceans. The first sedimentary rocks began accumulating in shallow marine basins, preserving a record of erosion and deposition that continues to this day. The early atmosphere remained profoundly different from the oxygen-rich envelope we breathe today, dominated by carbon dioxide, water vapor, and methane, with virtually no free oxygen. It created greenhouse conditions that kept the oceans liquid despite the sun being 30% weaker than its current luminosity. This solution to the faint young sun paradox required atmospheric carbon dioxide levels perhaps 100 times higher than today, creating a dense, steamy atmosphere that trapped heat with remarkable efficiency. Yet, even in these extreme conditions, the chemical foundations for life were being established. Hydrothermal vents on the seafloor created chemical gradients and energy sources that would prove crucial for the emergence of the first living organisms. The circulation of seawater through hot volcanic rocks generated complex organic molecules and concentrated essential elements like phosphorus and sulfur. By the end of the Hadean Eon, Earth had been transformed from a molten ball of rock into a water world with stable continents, active volcanism, and complex chemical cycles operating between ocean, atmosphere, and solid Earth. The stage was set for the next great transition, the emergence of life itself in the ancient seas. Hell had become high water, and in those primordial oceans, the greatest story in the history of our planet was about to begin. Life's first whispers. 3.8 to 2.5 billion years ago, hell had become high water, and in those primordial oceans, the greatest story in the history of our planet was about to begin. Yet the first chapters of this biological epic would be written not in grand, dramatic flourishes, but in whispers so faint they nearly escaped detection across the vast gulf of deep time. Hidden within the chemical signatures of ancient rocks, preserved in microscopic fossils, and encoded in the DNA of the simplest organisms alive today, lies evidence of life's earliest stirrings in a world that would have been utterly alien to modern eyes. The stage for life's emergence was unlike anything that exists on Earth today. The early Archean atmosphere contained less than 1/10,000th of the oxygen we breathe, dominated instead by methane, carbon dioxide, hydrogen, and ammonia. Volcanic activity operated on a scale that dwarfed anything in recorded history, with komatiite lavas erupting at temperatures exceeding 1,600 degrees Celsius. Yet within this seemingly hostile environment, the fundamental chemistry of life was taking shape. The earliest evidence of biological activity appears in rocks of staggering antiquity. In the Novouigetic greenstone belt of northern Quebec, scientists have discovered carbon isotope signatures in rocks dated to 3.95 billion years ago that bear the distinctive fingerprints of metabolic processes. These isotopic anomalies suggest that microorganisms were already consuming methane and cycling carbon through primitive ecosystems before the Earth had even finished cooling from its violent birth. Even more remarkably, structures found within these ancient formations may represent the fossilized remains of hydrothermal vents, underwater volcanic springs where superheated, mineral-rich water provided both energy and raw materials for the first living organisms. The chemistry of these environments, with their steep gradients of temperature, pH, and chemical composition, created natural laboratories where the complex molecules of life could form and interact. The first definitive fossils of life appear in rocks from Western Australia's Pilbara Craton, dated to approximately 3.5 billion years ago. These microscopic structures, preserved in chert formations with exquisite detail, show clear evidence of cellular organization and biological processes. The fossils reveal simple, prokaryotic cells, organisms lacking the complex internal structures of modern plants and animals, but possessing the fundamental machinery of life: DNA, ribosomes, and metabolic pathways. These earliest organisms belong to two great domains of life that persist today: bacteria and archaea. Despite their superficial similarity, these groups represent profoundly different solutions to the challenge of existence. Bacteria developed sophisticated cell walls and diverse metabolic strategies, while archaea specialized in surviving extreme environments: acidic hot springs, salt lakes, and anaerobic sediments that mimic the conditions of the early Earth. The most spectacular evidence of early life comes from structures known as stromatolites, layered, mounded formations created by communities of photosynthetic microorganisms. The oldest confirmed stromatolites, found in South Africa's Barberton Greenstone Belt, date to 3.48 billion years ago. These remarkable structures tell a story of cooperation and construction that predates any complex multicellular organism by billions of years. Stromatolites formed through a process both simple and profound. Photosynthetic bacteria, primarily cyanobacteria, grew in shallow marine environments where sunlight could penetrate the water. As these microorganisms photosynthesized, they altered the local chemistry of seawater, causing dissolved minerals to precipitate and cement sand grains around their filamentous bodies. Day after day, generation after generation, these tiny builders added layer upon layer, creating structures that could reach several meters in height. The peak of stromatolite abundance occurred around 1.25 billion years ago, when these microbial reefs dominated shallow marine environments worldwide. Their fossilized remains create some of Earth's most distinctive rock formations, with alternating bands of light and dark sediment recording ancient tidal cycles and seasonal variations. Yet by 700 million years ago, stromatolite abundance had declined dramatically, likely due to the evolution of grazing animals that could consume the microbial mats. The development of photosynthesis represents one of the most crucial innovations in the history of life. This process, which converts sunlight, carbon dioxide, and water into organic compounds and oxygen, would eventually transform Earth's entire atmosphere and make complex life possible. However, photosynthesis did not emerge in its modern form all at once. The first type to evolve, anoxygenic photosynthesis, appeared between 3.5 and 3.3 billion years ago. This primitive process used electron donors like hydrogen sulfide, hydrogen gas, or iron compounds rather than water, and produced no oxygen as a byproduct. These early photosynthetic organisms thrived in environments rich in sulfur and iron, creating the distinctive banded iron formations that characterize Archean marine sediments. The revolutionary innovation came with the evolution of oxygenic photosynthesis in cyanobacteria sometime between 3.4 and 2.9 billion years ago. This process split water molecules to provide electrons for photosynthesis, releasing oxygen as a waste product. Initially, this oxygen was quickly consumed by dissolved iron in seawater, preventing its accumulation in the atmosphere. But the stage was being set for one of the most dramatic environmental transformations in Earth's history. Cyanobacteria themselves tell a remarkable evolutionary story. Molecular clock studies suggest they branched from other bacterial lineages around 3.4 billion years ago, with their crown group, the common ancestor of all modern cyanobacteria, originating around 2.9 billion years ago. These organisms developed multicellularity around 2.3 billion years ago and underwent a major diversification burst around 2.4 billion years ago, coinciding with the Great Oxidation Event that would reshape the planet. The early Archean world operated under physical conditions that challenge our understanding of how life could survive and thrive. Despite the sun being 30% weaker than today, the famous faint young sun paradox, surface temperatures remained warm enough for liquid water through powerful greenhouse effects. Atmospheric concentrations of methane may have reached 1,000 times modern levels, while carbon dioxide levels were perhaps 100 times higher than today. This dense, reducing atmosphere created a greenhouse effect so powerful that it kept the oceans liquid despite the dim young Sunday methane-producing archaea, thriving in oxygen-free environments, pumped vast quantities of this potent greenhouse gas into the atmosphere. The interplay between biological methane production and atmospheric chemistry created a delicate balance that maintained habitable conditions for over 1 billion years. Continental crust stabilization during the Archean laid the foundation for increasingly complex ecosystems. The formation of cratons, ancient, stable portions of continental lithosphere, provided platforms for shallow marine environments where photosynthetic organisms could flourish. The Kopval Craton in South Africa and the Pilbara Craton in Western Australia, both formed between 3.6 and 2.7 billion years ago, preserve some of the best records of early life. Evidence suggests these cratons may have been joined in Earth's first supercontinent, Valbara, beginning around 3.6 billion years ago. Matching paleomagnetic orientations in volcanic rocks, similar geological sequences spanning 3.5 to 2.7 billion years, and identical meteorite impact signatures in both cratons support this reconstruction. The formation and breakup of such supercontinents would have profoundly influenced ocean circulation, climate patterns, and the distribution of early life. Throughout the Archean, life remained exclusively microbial, yet these simple organisms developed remarkable sophistication. They evolved complex metabolic pathways that could extract energy from virtually any available chemical source: sunlight, sulfur compounds, iron minerals, and organic matter. Some developed the ability to fix nitrogen from the atmosphere, while others formed intricate symbiotic relationships that previewed the evolution of complex cells. The end of the Archean Eon marked a critical threshold in Earth's history. Oxygen-producing cyanobacteria had been slowly building up their populations for hundreds of millions of years, while the planet's capacity to absorb oxygen through reaction with dissolved iron was reaching its limits. The stage was set for a transformation so dramatic it would constitute the first global environmental catastrophe and the first mass extinction in Earth's history. Life's first whispers had grown into a chorus powerful enough to reshape the planet itself. 6. The Great Poisoning. 2.5 to 1.8 billion years ago, life's first whispers had grown into a chorus powerful enough to reshape the planet itself. Yet the song these ancient microorganisms sang would prove to be a requiem, not just for the world they had known, but for the vast majority of life forms that had called Earth home for over a billion years. What began as the innocent waste product of photosynthesis would become the deadliest poison in planetary history, triggering the first mass extinction and fundamentally altering the chemistry of oceans, atmosphere, and rock formations across the globe. The catastrophe built slowly, invisibly, across hundreds of millions of years. Cyanobacteria, those remarkable organisms that had learned to split water molecules and harness the sun's energy, had been quietly releasing oxygen into Earth's ancient seas since at least 2.9 billion years ago. But this toxic gas, for toxic it was to nearly every form of life then existing, never accumulated in dangerous concentrations. The early Earth possessed an enormous capacity to absorb oxygen through chemical reactions with dissolved iron, sulfur compounds, and organic matter in the oceans. For nearly 500 million years, this delicate balance held. Every molecule of oxygen produced by photosynthesis was immediately consumed, mostly through reactions with ferrous iron dissolved in seawater. The process created distinctive rust-colored precipitates that settled to the seafloor, forming the banded iron formations that would become one of geology's most recognizable signatures of the Archean world. These alternating layers of iron oxide and silica tell a story of chemical cycling on a planetary scale, the metabolic rhythms of ancient oceans made visible in stone. But cyanobacteria populations were growing, spreading to every sunlit corner of the world's oceans, and their cumulative oxygen production was slowly overwhelming the planet's ability to neutralize this reactive gas. The tipping point came approximately 2.46 billion years ago, when atmospheric oxygen levels began their first dramatic rise from less than 1/10,000th of present concentrations to between 1% and 10% of modern levels. This transformation, known to scientists as the Great Oxidation Event, would prove to be the most dramatic environmental revolution in Earth's history. The rise of oxygen was not gradual or smooth. New research reveals it occurred through complex ecological dynamics involving competition between different microbial communities. When the ratio of iron influx to phosphate influx in ancient oceans fell below a critical threshold, cyanobacteria gained a decisive competitive advantage over anoxygenic photosynthetic bacteria that had dominated marine ecosystems for hundreds of millions of years. Simultaneously, declining nickel concentrations, essential for methanogen metabolism, reduced the production of methane, allowing oxygen to accumulate without being chemically consumed. The transformation was geochemically violent. Banded iron formations, which had characterized marine sedimentation for over a billion years, sharply declined as dissolved iron became oxidized and removed from seawater. Red beds, terrestrial sedimentary rocks rich in iron oxides, appeared for the first time in the geological record, painting continental landscapes in the rusty hues that would characterize oxidized environments. Sulfate minerals began forming in marine settings where sulfur had previously existed only in reduced forms, while the appearance of mass-independent sulfur isotope fractionation ended abruptly, a clear signal that atmospheric oxygen levels had risen high enough to create an ozone layer. Yet this environmental revolution came at a catastrophic cost. Oxygen was poison to the anaerobic organisms that had dominated Earth's biosphere for over a billion years. These ancient microbes had evolved sophisticated metabolisms based on the chemistry of a reducing world, environments rich in hydrogen, methane, hydrogen sulfide, and other compounds that react violently with oxygen. The Great Oxidation Event triggered the first mass extinction in Earth's history, eliminating countless species of bacteria and archaea that had no defense against the corrosive properties of this newly abundant gas. The extinction operated on multiple levels. Direct chemical poisoning killed organisms through the formation of reactive oxygen species that destroyed cellular components. Habitat destruction eliminated the anaerobic environments where these organisms thrived, as oxygen penetrated previously isolated refugia. Perhaps most devastatingly, the oxidation of atmospheric methane, a crucial greenhouse gas, triggered global cooling that may have contributed to some of Earth's earliest ice ages. The scale of biological devastation was unprecedented. Entire metabolic pathways that had sustained life for hundreds of millions of years became obsolete overnight in geological terms. Organisms that had evolved to extract energy from iron, sulfur, and organic compounds in oxygen-free environments found themselves in a world where their food sources had been chemically transformed into inedible forms. The evolutionary pressure was so intense that some scientists consider this event equivalent to a near-sterilization of the planet. Yet from this apparent catastrophe emerged opportunities that would ultimately enable the evolution of complex life. The organisms that survived the Great Oxidation Event either retreated to anaerobic refugia, deep sediments, hydrothermal vents, and the intestines of animals where they persist today, or evolved remarkable biochemical innovations to cope with oxygen's presence. Some developed antioxidant systems to neutralize oxygen's toxic effects, while others learned to use oxygen itself as a powerful energy source through aerobic respiration. Aerobic respiration represented a revolutionary advance in biological efficiency. While anaerobic metabolisms typically yield just 2 molecules of ADP from each glucose molecule, aerobic respiration produces 36 to 38 ATP molecules, nearly 20 times more energy from the same fuel. This dramatic increase in metabolic efficiency would prove crucial for the evolution of larger, more complex organisms that required substantial energy to maintain their cellular machinery. The transition was recorded in exquisite detail within sedimentary rocks worldwide. The Transvaal supergroup in South Africa preserves a continuous record of atmospheric oxygen evolution through changing mineral assemblages and isotopic signatures. Iron formations from this period show distinctive patterns of oxidation and reduction that reveal fluctuating oxygen levels as the atmosphere struggled to reach a new equilibrium. Carbon isotope records from the same period reveal the biological dimensions of the crisis. The ratio of carbon-13 to carbon-12 in ancient organic matter shifted dramatically, indicating massive changes in the global carbon cycle as methane-producing organisms declined and oxygen-producing cyanobacteria proliferated. These isotopic signatures provide a molecular-level view of ecosystem collapse and reconstruction operating on a planetary scale. The Great Oxidation Event also triggered the formation of some of Earth's most economically important mineral deposits. As oxygen reacted with dissolved metals in seawater and groundwater, it concentrated copper, uranium, gold, and other elements into or deposits that continue to be mined today. The famous Witwatersrand gold deposits of South Africa, among the richest ever discovered, formed during this period of atmospheric transformation. Climate effects of the oxygenation were profound and long-lasting. The oxidation of atmospheric methane removed a potent greenhouse gas, while the formation of an ozone layer altered atmospheric circulation patterns. These changes may have contributed to the Huronian glaciation, one of Earth's earliest known ice ages, which lasted from approximately 2.4 to 2.1 billion years ago and created some of the most extensive glacial deposits in the geological record. The event also fundamentally altered the evolution of Earth's continental crust. Oxygen enabled new styles of chemical weathering that broke down continental rocks more efficiently, delivering dissolved nutrients to the oceans while altering the composition of sedimentary rocks. The appearance of mature quartz sandstones and shales during this period reflects more intense weathering processes operating in an oxidizing atmosphere. By 1.8 billion years ago, atmospheric oxygen had stabilized at levels sufficient to support the evolution of larger, more complex organisms. The Great Oxidation Event had ended, leaving behind a planet transformed beyond recognition. The reducing atmosphere that had characterized Earth's first 2 billion years was gone forever, replaced by an oxidizing environment that would enable the evolution of multicellular life, complex ecosystems, and ultimately consciousness itself. The Great Poisoning had become the Great Liberation, setting the stage for life's next evolutionary breakthrough. 7. Snowball Earth. 1.8 to 0.6 billion years ago, the Great Poisoning had become the Great Liberation, setting the stage for life's next evolutionary breakthrough. Yet Earth's newly oxygenated atmosphere would soon face a test more severe than any in the planet's history. A trial by ice that would transform the blue marble into a cosmic snowball, entombing continents beneath glaciers miles thick and freezing the very oceans solid. What emerged from this frozen purgatory would be life itself, but not as it had ever existed before. The billion-year journey through Earth's most extreme climate crisis would forge the complexity that makes our modern biosphere possible. The stage for this cosmic deep freeze was set by the very oxygen revolution that had just concluded. As atmospheric oxygen levels stabilized between 1% and 10% of modern concentrations, the planet's climate system entered a new regime of unprecedented instability. The methane greenhouse that had kept Earth warm despite a weaker sun was largely gone, oxidized away by the reactive oxygen that now dominated the atmosphere. In its place, carbon dioxide became the primary greenhouse gas, but its concentrations were dropping as enhanced rock weathering in the new oxidizing atmosphere consumed CO2 faster than volcanoes could replenish it. The first signs of trouble appeared around 2.45 billion years ago with the Huronian glaciation, but this was merely a preview of the frozen catastrophes to come. As the Proterozoic Eon progressed, tectonic forces were reshaping the planet's surface in ways that would prove climatically disastrous. Continental masses were clustering toward equatorial regions, creating vast landmasses that reflected sunlight while disrupting ocean circulation patterns that had previously distributed heat around the globe. The crisis reached its zenith during 3 distinct episodes of global glaciation that would earn the name Snowball Earth. The first and longest was the Sturtian glaciation, which began around 720 million years ago and persisted for an almost incomprehensible 58 million years, longer than the entire Cenozoic era that has witnessed the rise of mammals and humans. During this frozen epoch, ice sheets advanced from both poles until they met at the equator, creating a planet wrapped in ice from pole to pole. Evidence for this extraordinary claim comes from rocks that preserve unmistakable signatures of glacial activity in locations that were unquestionably near the ancient equator. Diamictites, chaotic mixtures of boulders, sand, and clay dropped by melting glaciers, are found in paleomagnetic positions that place them within 10 degrees of the equatorial zone. These poorly sorted deposits, containing rocks carried hundreds of kilometers from their sources, tell of ice sheets powerful enough to scour continents and transport massive boulders across vast distances. The ice did not advance gradually. Paleoclimatic reconstructions reveal that once glaciation began, positive feedback mechanisms accelerated the cooling catastrophically. Fresh ice and snow reflected up to 90% of incoming solar radiation back to space, while the growing ice sheets lowered sea level and exposed more land to freeze. Ocean circulation slowed and eventually stopped as sea ice thickened, eliminating the transport of warm water from equatorial regions to higher latitudes. Within perhaps just a few thousand years, a geological instant Earth had transformed from a temperate world into a frozen wasteland with average global temperatures plummeting to minus 50 degrees Celsius. The ice sheets reached thicknesses of several kilometers, while sea ice extended to depths of at least 1 kilometer. The planet's albedo, its reflectivity, increased so dramatically that Earth became visible from space as a brilliant white sphere, earning its nickname as a cosmic snowball. Yet the most remarkable aspect of these glacial episodes was not their severity, but the fact that life survived them at all. As ice entombed the continents and sealed the oceans beneath kilometers of frozen water, photosynthesis essentially stopped on a global scale. The food webs that had sustained marine ecosystems for billions of years collapsed as sunlight could no longer penetrate the ice to reach photosynthetic organisms. Carbon isotope excursions during these periods show the most extreme negative values in Earth's history, indicating massive disruption of biological carbon cycling. How did life endure these seemingly apocalyptic conditions? The answer lies in hidden refugia that persisted even during the depths of snowball conditions. Hydrothermal vents on the seafloor continued operating beneath the ice, creating oases of liquid water heated by volcanic activity. These underwater hot springs supported communities of chemosynthetic bacteria that could extract energy from sulfur and iron compounds without requiring sunlight. Volcanic activity on land created temporary meltwater ponds around active eruptions, while geothermal areas generated ice-free zones where primitive life could persist. Some scientists propose that thin ice in certain regions allowed a limited amount of photosynthesis to continue, particularly in slush ball scenarios where the ice was not completely solid. Even more remarkably, recent research suggests that some cyanobacteria may have survived by entering dormant states, essentially hibernating through millions of years of frozen conditions. The deglaciation process was as dramatic as the initial freezing. With photosynthesis shut down and weathering essentially stopped by the global ice cover, volcanic carbon dioxide gradually accumulated in the atmosphere over millions of years. Climate models suggest that CO2 levels eventually reached 350 times present concentrations, creating a greenhouse effect so powerful that when melting finally began, it proceeded with explosive speed. The transition from snowball to greenhouse conditions may have occurred in less than 1,000 years. As dark ocean surfaces were exposed, they absorbed solar radiation and accelerated the melting process through the same feedback mechanisms that had driven the initial freezing. Global temperatures soared from -50 degrees Celsius to over 50 degrees Celsius, creating a super greenhouse world that persisted for millions of years after the ice disappeared. Evidence for these dramatic warming episodes comes from distinctive cap carbonates, limestone formations that directly overlie glacial deposits around the world. These rocks, precipitated from carbon dioxide-rich seawater during the post-glacial greenhouse conditions, contain some of the most negative carbon isotope signatures ever recorded, indicating massive perturbations to the global carbon cycle during deglaciation. The Sturtian glaciation was followed by the even more severe Marinoan glaciation, lasting from 645 to 635 million years ago. This second snowball episode may have been triggered by the breakup of the supercontinent Rodinia, which altered ocean circulation patterns and enhanced continental weathering that removed CO2 from the atmosphere. The final glacial episode, the Gaskiers glaciation around 580 million years ago, was shorter but still severe enough to leave global geological signatures. These repeated freeze-thaw cycles had profound evolutionary consequences. The extreme environmental pressures of snowball conditions favored organisms capable of surviving in refugia, leading to evolutionary innovations that would prove crucial for complex life. During the long intervals between glaciations, life underwent dramatic evolutionary experiments in the newly oxygenated oceans. The most significant development was the evolution of eukaryotic cells, organisms with complex internal structures including nuclei, mitochondria, and sophisticated cellular machinery. The earliest convincing eukaryotic fossils, acanthomorphic acritarchs from India, date to 1.631 billion years ago, but molecular clocks suggest these complex cells may have originated even earlier during the aftermath of the Great Oxidation Event. Eukaryotes represented a revolutionary leap in cellular complexity, achieved through a process Lynn Margulis called endosymbiosis. Larger cells engulfed smaller bacteria, which then became permanent residents providing specialized functions. Mitochondria, the powerhouses of modern cells, evolved from aerobic bacteria that enabled their hosts to exploit oxygen for energy production. Chloroplasts originated from cyanobacteria, allowing some eukaryotes to photosynthesize. The harsh conditions of snowball Earth episodes may have accelerated this evolutionary innovation by creating extreme selective pressures. Only the most adaptable and efficient organisms could survive the repeated environmental catastrophes, driving the evolution of increasingly sophisticated cellular machinery and metabolic flexibility. By 1.2 billion years ago, the first convincing evidence of sexual reproduction appears in the fossil record with Bangiomorpha pubescens, marking another crucial evolutionary breakthrough. Sex allowed organisms to rapidly reshuffle genetic material and adapt to changing environmental conditions, a capability that would prove essential for surviving future climate crises. The snowball Earth episodes finally ended around 580 million years ago, leaving behind a planet transformed yet again. The extreme climate fluctuations had tested life to its limits and forged new levels of cellular complexity. As stable, ice-free conditions returned, the The stage was set for the greatest evolutionary explosion in Earth's history. The frozen world was about to bloom with unprecedented diversity. 8. The Cambrian explosion. 541 to 485 million years ago, the frozen world was about to bloom with unprecedented diversity. As the last remnants of global ice sheets retreated into polar refugia, Earth's oceans began warming under greenhouse skies heavy with carbon dioxide. The Ediacaran period had witnessed the first tentative experiments in multicellular life, strange, quilted organisms that carpeted the seafloor like living geometry. But these primitive creatures were merely the opening notes of a biological symphony that would crescendo into the most dramatic evolutionary event in the planet's history. What happened next defied every expectation of gradual change that had characterized life's previous 3 billion years. In a span of time so brief it challenged Darwin himself, a mere 13 to 25 million years, the fossil record erupted with an explosion of complex animal forms that seemed to materialize from nowhere. Trilobites with compound eyes gazed across ancient seafloors. Predators with grasping appendages stalked through submarine forests of sponges. Creatures with shells, spines, and claws engaged in evolutionary arms races that would reshape the very nature of existence on Earth. This was the Cambrian explosion, and it represented nothing less than the invention of the animal kingdom as we know it. Between 20 and 35 major animal phyla, fundamental body plans that encompass everything from arthropods to chordates, made their first appearance in the fossil record during this geological instant. To comprehend the magnitude of this transformation, imagine the difference between a world populated only by bacterial mats and one suddenly teeming with whales, eagles, and tigers. The Cambrian accomplished an equivalent leap in complexity, but compressed into a time frame shorter than the extinction of the dinosaurs. The stage for this biological revolution had been set by environmental changes of unprecedented scale. Around 540 million years ago, atmospheric oxygen levels crossed a critical threshold that would prove essential for animal complexity. While still far below modern concentrations, oxygen had risen high enough to enable the production of collagen, the structural protein that allows animals to build hard shells, tough exoskeletons, and complex body parts. For the first time in Earth's history, organisms could construct protective armor and sophisticated appendages that opened entirely new ecological possibilities. Ocean chemistry underwent equally dramatic shifts that facilitated what scientists call biomineralization, the ability of organisms to precipitate minerals from seawater to build shells and skeletons. Declining iron concentrations, a legacy of the Great Oxidation Event, allowed calcium carbonate to reach saturation levels in shallow marine environments. This chemical change enabled animals to extract dissolved calcium and carbonate ions from seawater and combine them into the limestone structures that would revolutionize both predation and defense. The environmental triggers were necessary but not sufficient to explain the explosion's timing and intensity. Recent research suggests that the Cambrian explosion coincided with the emergence of increasingly sophisticated genetic control mechanisms, molecular toolkits that allowed organisms to build complex body plans with specialized organs and appendages. The evolution of Hox genes, which control body segment identity and appendage development, provided the genetic blueprint for constructing everything from the segmented bodies of arthropods to the notochords of early vertebrates. Yet perhaps the most significant innovation was the evolution of complex nervous systems and sophisticated sensory organs. The development of eyes, particularly the compound eyes of trilobites with their hundreds of calcite lenses, created the first visual arms race in Earth's history. Predators could now track prey across considerable distances, while prey species evolved increasingly elaborate defensive strategies including protective shells, burrowing behaviors, and chemical deterrence. The fossil record of this transformation is preserved with extraordinary fidelity in sites that rank among paleontology's greatest treasures. The Burgess Shale of British Columbia, discovered by Charles Walcott in 1909, provides a window into Cambrian marine ecosystems of almost impossible richness. Preserved in fine-grained sediments that captured soft tissues along with hard shells, the Burgess Shale fauna reveals a world of experimental body plans that challenge every assumption about early animal evolution. Among the most remarkable Burgess Shale organisms was Anomalocaris, a meter-long predator with flexible front appendages for grasping prey and a circular mouth lined with sharp teeth. This apex predator of Cambrian seas possessed compound eyes larger than dinner plates and a body plan unlike any modern animal, combining features that seem borrowed from arthropods, mollusks, and creatures that have no living analogs. Anomalocaris and its relatives represented evolutionary experiments in predation that pushed the boundaries of what was possible in ancient ecosystems. The Chengjiang deposits of southern China, slightly older than the Burgess Shale, preserve an even more complete record of early animal diversity. Among the thousands of exquisitely preserved fossils are the earliest known vertebrates, primitive fish-like creatures with simple notochords that would eventually give rise to the entire vertebrate lineage, including humans. These early chordates, including the enigmatic Haecoichthyes, possessed the fundamental body plan that would prove so successful it now dominates large animal ecosystems worldwide. Trilobites emerged as perhaps the most successful Cambrian animals, diversifying into hundreds of species that occupied every conceivable marine niche. These arthropods developed the first sophisticated compound eyes in the animal kingdom, with some species possessing visual systems containing over 15,000 individual lenses. The complexity of trilobite eyes rivals that of modern insects, yet these structures appeared fully formed in the earliest Cambrian rocks with no obvious evolutionary precursors, a pattern that initially seemed to support sudden creation rather than gradual evolution. The mystery deepened when paleontologists discovered that many Cambrian animals possessed body plans that have no modern equivalents. Wawaxia, covered in scales and spines, combined features of mollusks and annelid worms in ways that suggest experimental evolutionary pathways that were later abandoned. Opabinia sported 5 mushroom-shaped eyes and a flexible proboscis tipped with a grasping claw, a body plan so bizarre that early paleontologists struggled to determine which end was the front. This proliferation of experimental forms reflects what evolutionary biologists call morphological disparity. The range of different body plans present in ancient ecosystems actually exceeded the diversity seen in modern seas. The Cambrian was not just an explosion of species numbers but an explosion of evolutionary creativity, as life experimented with ways of being an animal that have never been repeated. The driving forces behind this creative explosion operated on multiple levels simultaneously. The evolution of predation created selective pressures that favored both offensive and defensive innovations, leading to escalating arms races between hunters and hunted. The development of complex ecosystems with multiple trophic levels allowed for ecological specialization that supported greater overall diversity. Most fundamentally, the genetic and developmental innovations of early animals had opened a vast landscape of morphological possibilities that evolution was rapidly exploring. Burrowing behaviors, first widespread during the late Ediacaran, intensified during the Cambrian as animals sought refuge from increasingly sophisticated predators. This bioturbation, the mixing of sediments by burrowing organisms, fundamentally altered seafloor chemistry and created new ecological niches within the sediment itself. The three-dimensional utilization of marine habitats added new complexity to ecosystems that had previously been confined largely to seafloor surfaces. The first reefs appeared during the Cambrian, built not by corals but by peculiar organisms called archaeocyathids. These sponge-like creatures constructed elaborate calcium carbonate frameworks that provided habitat for countless other organisms while creating some of Earth's first complex three-dimensional ecosystems. Though archaeocyathids went extinct by the end of the Cambrian, they established the ecological template for reef ecosystems that continues today. By the end of the Cambrian explosion, the fundamental architecture of animal life had been established. Every major animal phylum present in modern oceans had representatives in Cambrian seas, along with several experimental lineages that would later disappear. The biological revolution was complete, leaving behind a planet permanently transformed by the presence of complex, active, intelligent life. The age of animals had begun, and there would be no turning back. 9. Conquering the land. 450 to 300 million years ago, the age of animals had begun, and there would be no turning back. Yet for all the explosive creativity of the Cambrian seas, life remained confined to the ancient realm of water where it had first stirred over 3 billion years earlier. Above the waves stretched a world of impossible harshness, a landscape scoured by unfiltered ultraviolet radiation, baked by temperature extremes, and utterly devoid of the chemical stability that water provided. For hundreds of millions of years, The continents had remained barren stone, lifeless as the surface of Mars. But life had learned to dream of shores. Deep in the coastal shallows, where freshwater streams met the salt embrace of ancient seas, evolutionary pressures were building toward one of the most momentous transitions in the planet's history. The conquest of land would require nothing less than the complete reinvention of how to exist, new strategies for obtaining water, nutrients, and energy in an environment that had never known the touch of living cells. The first pioneers were not animals but an unlikely partnership between plants and fungi that would reshape the very nature of terrestrial environments. Around 450 million years ago, simple green algae began venturing beyond the margins of ponds and streams, their cellular machinery slowly adapting to the crushing challenges of atmospheric existence. They faced obstacles that would have seemed insurmountable. The constant threat of desiccation, the absence of dissolved nutrients, and the deadly bombardment of solar radiation in an atmosphere still largely lacking a protective ozone layer. Fungi proved to be life's most crucial allies in this terrestrial assault. These remarkable organisms, neither plant nor animal but something entirely their own, possessed biochemical arsenals perfectly suited for breaking down rock and extracting nutrients from mineral substrates. Their thread-like hyphal networks could penetrate stone itself, secreting acids that dissolved granite and basalt into their constituent elements. What emerged from this patient chemical warfare was something previously unknown on Earth's surface: soil. The collaboration between plants and fungi created one of biology's most successful partnerships. Mycorrhizal associations, intimate connections between fungal networks and plant roots, allowed early land plants to access nutrients across vast underground territories while providing fungi with the sugars and organic compounds that only photosynthesis could produce. This ancient alliance continues today, with over 90% of land plants maintaining fungal partnerships that are essential for their survival. The earliest confirmed vascular plant, Cooksonia, appeared around 420 million years ago during the Silurian period. These primitive pioneers stood only a few centimeters tall, their simple branching stems topped with reproductive structures called sporangia that released clouds of spores into the wind. Cooksonia lacked true leaves or roots, instead relying on simple surface absorption and basic vascular tissues to transport water and nutrients through their tiny bodies. Yet these humble beginnings concealed revolutionary innovations that would transform the planet. The evolution of lignin, a complex polymer that provides structural support, enabled plants to grow upward towards sunlight while maintaining their shape against gravity's pull. The development of cuticles, waxy surface coatings that reduced water loss, allowed survival in the desiccating atmosphere. Most crucially, the evolution of stomata, microscopic pores that could open and close, gave plants control over gas exchange, enabling them to photosynthesize while conserving precious water. Animal colonization of land proceeded along multiple pathways, with arthropods leading the charge around 450 million years ago. These animals possessed crucial advantages that made terrestrial existence possible. Exoskeletons that provided both structural support and protection from desiccation, sophisticated respiratory systems that could extract oxygen from air rather than water, and behavioral adaptations that allowed them to avoid the most deadly aspects of the terrestrial environment. The first land animals were likely myriapods, millipedes, and centipedes whose segmented bodies and numerous legs provided stability on uneven terrestrial surfaces. These pioneering arthropods fed on decaying plant matter and smaller organisms, establishing the foundation of terrestrial food webs. They were followed by arachnids, including scorpions and primitive spiders, which brought predation to the continents for the first time in Earth's history. The transition from water to land was not merely a matter of physiological adaptation but required fundamental changes in reproductive strategies. Aquatic animals had relied on water to transport sperm to eggs and to provide a protective medium for developing embryos. Terrestrial reproduction demanded new solutions: internal fertilization, protective egg casings, and parental care behaviors that ensured offspring survival in the harsh atmospheric environment. The Devonian period, spanning from 419 to 359 million years ago, witnessed what paleobotanists call the plant revolution, a transformation so complete it earned the Devonian its nickname as the Age of Fishes and Forests. By 385 million years ago, the first true forests appeared on Earth's surface, dominated by Archaeopteris, remarkable trees that combined fern-like leaves with woody trunks and could reach heights of 30 meters with trunk diameters exceeding 1 meter. These ancient forests created entirely new environmental conditions that had never existed in Earth's history. The extensive root systems of early trees accelerated rock weathering on a planetary scale, drawing down atmospheric carbon dioxide and contributing to global cooling that would eventually culminate in ice ages. Forest canopies created shaded microclimates that moderated temperature extremes and retained moisture, enabling the evolution of smaller, more delicate organisms that could never have survived on the barren continents. The complexity of these early ecosystems is preserved in remarkable detail at sites like the Riney Chert in Scotland, where 407-million-year-old hot spring deposits contain some of the oldest known terrestrial fossils. These ancient silica formations preserve cellular details of early land plants, fungi, and arthropods, revealing intricate ecological relationships including the earliest known examples of plant-animal interactions and sophisticated food webs operating on dry land. Among the most significant Devonian discoveries was Tiktaalik, the famous fishapod, found in 375-million-year-old rocks of the Canadian Arctic. This extraordinary creature possessed both gills and primitive lungs, fins with robust internal bones capable of supporting weight on land, and a flattened skull with eyes positioned on top. Adaptations perfect for a life spent in shallow water with occasional ventures onto mudflats and riverbanks. Tiktaalik represents one of evolution's most important transitional forms, bridging the gap between fully aquatic fish and the first tetrapods, four-limbed vertebrates that would eventually give rise to all land vertebrates, including humans. The creature's discovery validated predictions made by evolutionary biologists about what transitional forms should look like and where they might be found, demonstrating the predictive power of evolutionary theory in understanding life's history. The late Devonian witnessed the evolution of seeds, perhaps the most important innovation in plant evolution since photosynthesis itself. Unlike spores, which required water for fertilization and provided no nourishment for developing embryos, seeds contained everything necessary for successful reproduction in terrestrial environments: protective coatings, stored nutrients, and embryos that could remain dormant until conditions became favorable for growth. Seed plants revolutionized terrestrial ecosystems by enabling colonization of increasingly arid environments and seasonal climates where water availability fluctuated dramatically. The evolution of pollen grains, male reproductive cells that could be transported by wind rather than requiring water for fertilization, freed plant reproduction from dependence on aquatic environments entirely. By the end of the Carboniferous period around 300 million years ago, vast swamp forests dominated by seed ferns, early conifers, and giant club mosses covered much of the planet's land surface. These forests were so extensive and productive that their buried remains would eventually become the coal deposits that powered human civilization's industrial revolution. The terrestrial biosphere had achieved complexity rivaling that of marine ecosystems, with sophisticated predator-prey relationships, complex food webs, and intricate symbiotic partnerships. The conquest of land was complete, but it had come at a cost. The same innovations that enabled terrestrial existence, particularly the evolution of extensive root systems and the weathering of continental rocks, had dramatically altered Earth's climate system. Atmospheric carbon dioxide levels plummeted as organic carbon became buried in terrestrial sediments, while increased weathering rates consumed CO2 through chemical reactions with silicate minerals. The stage was set for one of Earth's most severe climate crises, a global cooling event that would test the resilience of these newly terrestrial ecosystems and drive evolution toward even greater complexity and adaptability. The Great Dying. 252 million years ago, the stage was set for one of Earth's most severe climate crises. But what came next exceeded every nightmare that evolution had yet conceived. Deep beneath the Siberian continent, forces were stirring that would make the Cambrian explosion seem gentle by comparison. In the span of just 60,000 years, a geological heartbeat, life on Earth would face an extinction so severe that it nearly ended the story of complex organisms entirely. This was not merely another mass extinction, but the closest our planet has ever come to complete biological collapse. The late Permian world of 252 million years ago bore little resemblance to the Earth we know today. All the major continents had coalesced into a single, massive supercontinent called Pangaea, stretching from pole to pole and creating the largest landmass in Earth's history. Vast interior deserts baked under intense heat, while the enormous Panthalassic Ocean covered most of the planet's surface. Life had achieved remarkable diversity both on land and in the sea, with complex ecosystems supporting everything from primitive reptiles to elaborate reef communities built by rugose corals and brachiopods. Yet beneath this apparent stability, the planet was primed for catastrophe. The continental collision that created Pangaea had altered global circulation patterns, while the supercontinent's geography created extreme seasonal variations and massive monsoon systems. Perhaps most ominously, deep beneath what is now Siberia, one of the largest volcanic systems in Earth's history was building toward an eruption that would reshape the planet's surface and atmosphere. The Siberian Traps, named for the distinctive stepped landscape created by layered volcanic rocks, represent one of the most massive volcanic events in Earth's history. The eruptions began gradually around 252.2 million years ago, but within a few thousand years had escalated into a volcanic apocalypse that defied comprehension. Lava flows covered an area larger than Western Europe to depths exceeding 3 kilometers in places, while volcanic gases and ash transformed the atmosphere and poisoned ecosystems worldwide. The scale of the eruptions staggers the imagination. Conservative estimates suggest the Siberian Traps erupted over 3 million cubic kilometers of lava, enough to bury the entire continental United States under a layer 400 meters thick. The eruptions operated on timescales that human experience cannot encompass, with individual lava flows extending over 1,500 kilometers and maintaining temperatures above 1,200 degrees Celsius for months or years. But it was not the lava itself that triggered the extinction, it was the gases. The Siberian eruptions released unprecedented quantities of carbon dioxide, sulfur dioxide, hydrogen chloride, and other volcanic gases into the atmosphere. Carbon dioxide concentrations may have increased by a factor of 7, creating greenhouse conditions more extreme than any in Earth's subsequent history. Global temperatures soared by 10 to 15 degrees Celsius, transforming most of the planet into a hellish wasteland where few organisms could survive. The warming was only the beginning of a cascade of environmental disasters that compound each other with terrifying efficiency. As temperatures rose, the solubility of oxygen in seawater decreased dramatically, creating vast oceanic dead zones where only anaerobic bacteria could survive. Ocean chemistry shifted toward acidic conditions as volcanic gases dissolved in seawater, making it impossible for shell-building organisms to extract calcium carbonate from the increasingly corrosive water. Hydrogen sulfide gas, produced by anaerobic bacteria thriving in the oxygen-depleted oceans, began bubbling up from the depths and poisoning the atmosphere. This toxic gas, which smells of rotten eggs and is lethal to most complex organisms, may have reached concentrations in the atmosphere sufficient to cause direct poisoning of terrestrial life. The protective ozone layer was damaged by volcanic emissions, allowing deadly ultraviolet radiation to sterilize large portions of the planet's surface. The extinction proceeded with relentless efficiency. In the oceans, 96% of all species disappeared forever, the highest extinction rate in Earth's history. Entire groups of organisms that had dominated marine ecosystems for hundreds of millions of years vanished without trace. The rugose and tabulate corals that had built vast reef systems were eliminated entirely. Trilobites, those supremely successful arthropods that had survived every previous crisis for nearly 300 million years, finally succumbed to extinction. Brachiopods, which had dominated seafloor communities since the Cambrian, lost 90% of their diversity and never recovered their former prominence. The extinction was so thorough that it eliminated not just species but entire ecological guilds, ways of making a living that had persisted since complex life began. The marine realm was reduced to a simplified ecosystem dominated by disaster taxa, opportunistic organisms that could survive in the harsh post-extinction environment. On land, the devastation was equally severe though less well documented due to the sparser terrestrial fossil record. Approximately 70% of terrestrial vertebrate species disappeared, including many of the synapsids, the mammal-like reptiles that had achieved remarkable diversity during the Permian. Forests collapsed as plant communities were overwhelmed by heat, drought, and acid rain. Soil systems broke down as the organisms that maintained them died off, creating vast badlands where erosion stripped away the organic substrates that had taken millions of years to accumulate. Perhaps most remarkably, the Permian-Triassic extinction was the only major extinction event to significantly affect insects, organisms so adaptable they had survived every previous crisis essentially unscathed. The fact that even insects suffered massive losses speaks to the unprecedented severity of the environmental changes triggered by the Siberian eruptions. Recent research has revealed that the extinction operated on multiple timescales, with rapid initial phases followed by prolonged environmental instability that prevented recovery for millions of years. The initial killing phase lasted perhaps 60,000 years, fast enough that individual volcanic eruptions contributed to the crisis, but long enough that multiple feedback mechanisms amplified the destruction. Ocean acidification, global warming, oxygen depletion, and atmospheric poisoning created a perfect storm of environmental stresses that overwhelmed even the most adaptable organisms. The aftermath was equally extraordinary. For the first time in over 200 million years, complex reef ecosystems completely disappeared from the fossil record. The early Triassic world was dominated by microbial mats reminiscent of Precambrian environments, a shocking regression to simpler ecological states that had not been seen since before the rise of complex life. Recovery was agonizingly slow, with ecosystem complexity taking over 10 million years to return to pre-extinction levels. Yet from this apparent biological catastrophe emerged opportunities that would reshape the evolutionary trajectory of life on Earth. The extinction eliminated dominant groups that might have prevented the rise of new organisms, opening ecological niches for previously marginal lineages to diversify and experiment with new ways of living. Among the survivors were small archosaurs, reptiles that would eventually give rise to dinosaurs and transform terrestrial ecosystems throughout the Mesozoic era. The Great Dying also marked a fundamental transition in ocean chemistry and ecosystem structure. The elimination of Paleozoic marine communities paved the way for the Mesozoic marine revolution, the evolution of increasingly sophisticated predators and prey that would drive the arms races characteristic of modern marine ecosystems. Bivalves began their rise to dominance over brachiopods, while new types of predatory gastropods and crustaceans evolved strategies for crushing heavily armored prey. Perhaps most significantly, the extinction reset the evolutionary clock in ways that would prove crucial for mammalian evolution. The synapsids that dominated Permian terrestrial ecosystems were largely eliminated, but among the survivors were small forms that would eventually give rise to the first true mammals. Had the extinction not occurred, mammals might never have evolved beyond small, nocturnal creatures overshadowed by their synapsid relatives. As the Triassic period dawned around 251 million years ago, Earth began its slow recovery from the greatest catastrophe in the history of complex life. The planet that emerged from the ashes would be profoundly different, set on an evolutionary trajectory that would lead to dinosaur dominance, flowering plant diversity, and ultimately the rise of mammals and human consciousness. The Great Dying had ended, but its legacy would shape the next chapter of life's story for hundreds of millions of years to come. 11. Age of Giants. 252 to 66 million years ago, the Great Dying had ended, but its legacy would shape the next chapter of life's story for hundreds of millions of years to come. From the ashes of the greatest catastrophe in Earth's history, a new world was about to emerge, one that would witness the rise of creatures so magnificent and terrible they continue to capture human imagination 66 million years after their disappearance. This was the dawn of the Mesozoic era, the age when giants would walk the earth and life would experiment with size, ferocity, and beauty on scales never before attempted. The early Triassic world that emerged from the Permian extinction bore little resemblance to the vibrant ecosystems that had preceded it. Vast stretches of barren landscapes stretched across the supercontinent Pangaea, while simplified marine communities struggled to rebuild from the biological wasteland left by the Siberian traps volcanism. For nearly 10 million years, Earth's ecosystems remained locked in a state reminiscent of much earlier geological eras, dominated by microbial mats and disaster taxa that could survive in the harsh, unstable environment. Yet among the survivors of the Great Dying lay the seeds of a biological renaissance that would transform the planet beyond recognition. Small archosaurs, reptiles characterized by distinctive skull openings and sophisticated jaw muscles, had weathered the extinction in marginal environments where their modest size and efficient metabolisms provided crucial advantages. These humble survivors possessed evolutionary potential that the devastated world was finally ready to unleash. The recovery began slowly, almost imperceptibly, around 240 million years ago as climate conditions stabilized and ecosystems regained their complexity. The archosaurs split into two great lineages that would define terrestrial life for the next 180 million years. One branch gave rise to the crocodilians, which would perfect an ambush predator lifestyle so successful it has remained essentially unchanged to the present day. The other branch evolved into something unprecedented in Earth's history: the dinosaurs. The first dinosaurs appeared around 235 million years ago during the Middle Triassic, but these early forms bore little resemblance to the giants that would later dominate the planet. Creatures like Eoraptor and Staurikosaurus stood no taller than a large dog, with slender builds adapted for speed rather than size. Yet they possessed revolutionary anatomical innovations that would prove crucial for their eventual success. Upright limbs that supported their bodies efficiently, sophisticated hip structures that enabled powerful locomotion, and metabolic adaptations that may have included some degree of warm-bloodedness. For nearly 30 million years, dinosaurs remained relatively minor components of Triassic ecosystems, overshadowed by other archosaur groups including the heavily armored Aetosaur and the massive predatory Rauisuchids. The world was still dominated by mammal-like reptiles that had survived the extinction, while early mammals, tiny, nocturnal creatures no larger than shrews, scurried through the underbrush in search of insects and seeds. Everything changed with the end Triassic extinction 201 million years ago. This crisis, triggered by massive volcanic eruptions that formed the Central Atlantic Magmatic Province, eliminated approximately 80% of species and cleared ecological niches that dinosaurs were perfectly positioned to exploit. The extinction removed the large archosaur competitors that had suppressed dinosaur diversity, while climate changes favored the metabolic advantages that dinosaurs had developed during their long apprenticeship in marginal environments. The Jurassic period that followed witnessed one of the most remarkable evolutionary radiations in Earth's history. Freed from competition, dinosaurs exploded into virtually every terrestrial ecological niche, evolving forms so diverse they challenged the very concept of what it meant to be a reptile. In the warm, humid greenhouse conditions of the Jurassic world, some lineages pursued a strategy of gigantism that produced the largest land animals in Earth's history. The sauropods epitomized this trend toward colossal size. Creatures like Brachiosaurus, Diplodocus, and Apatosaurus reached lengths exceeding 25 meters and weights approaching 80 tons, dimensions that pushed the physical limits of terrestrial vertebrate design. These giants possessed numerous anatomical innovations that made their enormous size possible. Hollow bones that reduced weight while maintaining strength, extremely long necks that allowed them to browse vegetation across vast areas without moving their massive bodies, and sophisticated cardiovascular systems capable of pumping blood to heads held 15 meters above their hearts. The evolutionary advantages of such extreme size are still debated by paleontologists, but likely included protection from predators, access to food sources unavailable to smaller animals, and thermal regulation benefits in the warm Mesozoic climate. The largest sauropods may have been essentially immune to predation as adults, their sheer bulk making them invulnerable to even the most formidable theropod predators. Yet dinosaurs achieved far more than impressive size. They pioneered sophisticated social behaviors that rivaled those of modern mammals. Fossil evidence reveals extensive nesting colonies where dinosaurs engaged in parental care, bringing food to their young and protecting them from predators. Some species like Maiasaura built elaborate nests lined with vegetation that generated heat through decomposition, effectively incubating their eggs through biological fermentation. The diversity of dinosaur forms defied easy categorization. Theropods evolved from small, agile predators into giants like Allosaurus and the massive Tyrannosaurus rex, which would not appear until the Cretaceous. Ornithischians developed elaborate defensive strategies including the armored plating of ankylosaurs, the fearsome spikes of stegosaurs, and the complex social structures of ceratopsians with their spectacular frilled skulls and facial horns. Perhaps most remarkably, some theropods began experimenting with flight. The famous Archaeopteryx, discovered in 150-million-year-old Bavarian limestone, possessed both primitive feathers and reptilian features like teeth and a long bony tail. This creature, caught in the evolutionary transition between dinosaur and bird, revealed that dinosaurs had not only conquered land but were beginning to master the skies as well. The Cretaceous period, spanning from 145 to 66 million years ago, witnessed peak dinosaur diversity alongside a botanical revolution that would transform terrestrial ecosystems permanently. Around 125 million years ago, flowering plants, angiosperms, made their first appearance in the fossil record. Within just 45 million years, these remarkable organisms had achieved global dominance, fundamentally altering the appearance and function of land-based ecosystems. The angiosperm revolution represented more than just the evolution of flowers and fruit. These plants developed sophisticated partnerships with insects that created some of nature's most intricate coevolutionary relationships. Bees, butterflies, and countless other pollinators evolved specialized morphologies and behaviors to exploit floral resources, while plants developed increasingly elaborate strategies to attract and reward their animal partners. The impact on dinosaur evolution was profound. The radiation of flowering plants created new food sources that supported herbivorous dinosaur diversity during the late Cretaceous. Ceratopsians like Triceratops evolved powerful jaw muscles and sophisticated dental batteries to process tough angiosperm foliage, while hadrosaurs developed complex nasal passages that may have enhanced their ability to detect chemical signals from flowering plants. Predatory dinosaurs reached their evolutionary zenith during the Cretaceous. Tyrannosaurus rex, perhaps the most famous dinosaur of all, combined massive size with sophisticated sensory systems and bone-crushing bite forces that could exceed 12,000 pounds per square inch. Recent research suggests T. rex possessed remarkable binocular vision and an acute sense of smell that made it one of the most formidable predators in Earth's history. Yet even as dinosaurs achieved unprecedented diversity and sophistication, forces were building that would bring their reign to a catastrophic end. In what is now Mexico's Yucatan Peninsula, an asteroid with a diameter of approximately 10 kilometers was hurtling through space on a collision course with Earth. This cosmic projectile, traveling at 20 kilometers per second, carried enough kinetic energy to end the Mesozoic era and usher in the Age of Mammals. The late Cretaceous world showed no signs of the impending catastrophe. Dinosaur diversity was at its peak, with new species continuing to evolve and expand into novel ecological niches. The global climate remained warm and stable, supporting lush forests and extensive inland seas. Yet within the rock record, traces of massive volcanism in India's Deccan Traps hint at environmental stresses that may have already begun weakening ecosystems before the final blow arrived. The Age of Giants was approaching its end, though none of the magnificent creatures that dominated the late Cretaceous world could have anticipated the cosmic accident that would reshape life's trajectory once again. In just a few million years, the longest-running evolutionary experiment in terrestrial vertebrate gigantism would be terminated with shocking suddenness, clearing the stage for an entirely different cast of characters to inherit the Earth. 12. The Asteroid's Judgment. 66 million years ago, the Age of Giants was approaching its end, though none of the magnificent creatures that dominated the late Cretaceous world could have anticipated the cosmic accident that would reshape life's trajectory once again. On what began as an ordinary day 66 million years ago, beneath skies where pterosaurs soared and across landscapes where Triceratops grazed peacefully among flowering meadows, a messenger of annihilation was screaming toward Earth through the vacuum of space. In the span of mere seconds, this cosmic projectile would end the longest-running evolutionary experiment in terrestrial gigantism and usher in an entirely new chapter in the planet's biological history. The impactor, a mountain-sized asteroid or comet nucleus approximately 10 kilometers in diameter, had been wandering the solar system for billions of years before gravitational perturbations sent it careening toward Earth. Traveling at 20 kilometers per second, this chunk of rock and metal carried the kinetic energy of roughly 10 billion atomic bombs, sufficient to vaporize entire mountain ranges and reshape continents. Its destination was a shallow tropical sea in what would one day become Mexico's Yucatan Peninsula, a location that would prove catastrophically perfect for maximizing global destruction. The moment of impact, at precisely 66.043 million years ago, according to radiometric dating of the event's geological signature, marked one of the most precisely timed catastrophes in Earth's history. The asteroid struck the sulfur-rich limestone and gypsum deposits of the Yucatan Shelf with such violence that it instantly vaporized both the impactor and thousands of cubic kilometers of target rock, creating a fireball that briefly outshone the sun and excavated the Chicxulub crater. A scar 180 kilometers across that would remain hidden beneath younger sediments until gravity surveys revealed its presence in the 1990s. The physics of the impact defied terrestrial experience. Within the first second, rock behaved like liquid as shock waves propagated outward at velocities exceeding 10 kilometers per second. The initial crater, excavated in just minutes, reached depths of 30 kilometers before rebounding to create a complex ring structure that permanently deformed the Earth's crust. Massive chunks of vaporized rock were hurled beyond the atmosphere, some achieving escape velocity and leaving the Earth-Moon system entirely, while others followed ballistic trajectories that would rain molten debris across the entire planet. The immediate devastation extended far beyond the impact site. Seismic waves equivalent to a magnitude 11 earthquake, more powerful than any seismic event in recorded history, rippled across the planet's surface, triggering landslides, tsunamis, and volcanic eruptions thousands of kilometers away. In the Gulf of Mexico, impact-generated tsunamis reached heights exceeding 100 meters, scouring the seafloor and hurling marine sediments hundreds of kilometers inland. The distinctive spheral beds, containing tiny glass beads formed from condensed impact vapor, can be traced across North America, providing a permanent record of this cosmic catastrophe. Yet, the most devastating effects were still to come. The impact had blasted enormous quantities of sulfur-rich rock into the stratosphere, where it formed sulfuric acid aerosols that blocked sunlight on a global scale. Temperatures plummeted as much as 26 degrees Celsius in some regions, while acid rain with the corrosiveness of battery acid fell from toxic skies. The impact had occurred in one of the worst possible locations. Had the asteroid struck virtually anywhere else on Earth, the sulfur content of the target rocks would have been much lower, and the climatic effects correspondingly less severe. Photosynthesis essentially stopped across most of the planet as sunlight levels dropped to less than 1% of normal. The impact winter lasted for months or perhaps years, during which time food webs collapsed from the bottom up as primary producers died off and the energy that sustained complex ecosystems simply vanished. In the darkness and cold that followed, the age of dinosaurs came to its end not with the dramatic battles depicted in popular culture, but with starvation, hypothermia, and the gradual breakdown of ecosystems that had supported these magnificent creatures for 165 million years. The extinction was breathtakingly selective in its victims. Non-avian dinosaurs, which had survived numerous previous crises and diversified into hundreds of species, were eliminated entirely. Pterosaurs, the masters of Mesozoic skies, vanished without trace. Marine reptiles, including plesiosaurs and mosasaurs, disappeared from the oceans, along with the ammonites that had been among the most successful marine animals for over 300 million years. In total, approximately 76% of all species on Earth were eliminated, making this the second most severe extinction in the planet's history. Yet the pattern of survival and extinction revealed crucial insights about what determined an organism's fate during this global catastrophe. Small body size proved overwhelmingly advantageous. Few animals larger than 25 kilograms survived the impact winter. The ability to enter dormancy, whether through hibernation, estivation, or seed formation, provided crucial protection during the months of darkness and cold. Organisms that could survive on detritus and decomposing organic matter fared better than those dependent on living plant material, while freshwater environments offered more refuge than marine habitats. Birds, which are, scientifically speaking, dinosaurs that survived, made it through the extinction bottleneck, though they lost most of their diversity and were reduced to small, ground-dwelling forms that could exploit seeds and other dormant food sources. Mammals, which had spent 100 million years as small, nocturnal creatures overshadowed by their reptilian contemporaries, suddenly found themselves inheriting a world with dramatically reduced competition and countless vacant ecological niches. The extinction event was not solely the work of the asteroid impact. Throughout the late Cretaceous, massive volcanic eruptions in what is now India's Deccan Traps had been pumping enormous quantities of lava, ash, and toxic gases into the atmosphere. These eruptions, among the largest in Earth's history, had already begun stressing global ecosystems through climate warming, acid rain, and atmospheric pollution. The asteroid impact delivered the final blow to ecosystems already weakened by sustained volcanism. Evidence for this double catastrophe is preserved in rock formations worldwide. The iridium anomaly, a thin layer of sediment enriched in this rare metal that is abundant in asteroids but scarce in Earth's crust, marks the precise moment of impact in geological sections across the globe. Below this layer lie the last fossils of non-avian dinosaurs, while above it stretches a world dominated by ferns, small mammals, and the survivors of Earth's fifth great mass extinction. The recovery that followed would reshape the planet's biological landscape completely. With large reptilian predators eliminated, mammals began an evolutionary radiation that would ultimately produce creatures as diverse as whales, bats, elephants, and humans. Flowering plants, which had suffered severe losses during the impact winter, rebounded to achieve even greater dominance in post-extinction ecosystems. The warm-blooded, intelligent, socially complex creatures that would eventually evolve the capacity to understand their own cosmic history owed their existence to this moment of celestial violence. The asteroid's judgment was final and irreversible. The age of reptilian giants was over, ended not by competitive failure or gradual environmental change, but by a cosmic accident that demonstrated the fragility of even Earth's most successful evolutionary experiments. In the rubble of the old world, a new biological order was about to emerge, one that would eventually produce creatures capable of looking back across deep time and understanding the very catastrophe that had made their existence possible. The mammal's moment had arrived. 13. Ice and ancestors. 66 million years ago present. The mammal's moment had arrived. In the eerie silence that followed the asteroid's judgment, Earth resembled a planet in mourning. Vast forests lay buried under layers of impact debris, while toxic clouds still shrouded the sky in perpetual twilight. Yet in this apparent wasteland, something extraordinary was stirring. From the underground burrows and hidden refugia where they had waited out the cosmic catastrophe, small warm-blooded creatures emerged to inherit a world transformed beyond recognition. For over 100 million years, mammals had lived as evolutionary bit players in the grand drama of the Mesozoic. Constrained to nocturnal lifestyles by day-active dinosaurs, most had remained smaller than house cats, subsisting on insects, seeds, and whatever scraps they could scavenge from the giants that ruled their world. But the KPG extinction had reset the evolutionary game board completely, eliminating every land animal larger than 25 kilograms and opening ecological niches that had been monopolized by reptiles since the Triassic. The early Paleocene world that emerged from the extinction bottleneck bore little resemblance to either the dinosaur-dominated ecosystems that preceded it or the complex mammalian communities that would follow. For nearly 10 million years, recovery proceeded slowly as ecosystems rebuilt themselves from the ground up. Ferns dominated the plant communities in many regions. These ancient survivors had weathered the impact winter by retreating to underground rhizomes and were among the first to reclaim the devastated landscapes. Among the mammalian survivors, a few key lineages possessed evolutionary potential that the post-extinction world was ready to unleash. The placental mammals that nourished their young through sophisticated placental connections had evolved advanced reproductive strategies that proved crucial for exploiting the vacant niches left by extinct dinosaurs. Unlike the egg-laying monotremes or the pouch-bearing marsupials, placental mammals could invest heavily in their offspring's development before birth, producing young that were better equipped to survive in the harsh post-extinction environment. The mammalian radiation that followed ranks among the most spectacular evolutionary explosions in Earth's history. Within just 10 to 15 million years after the extinction, mammals had diversified from a handful of small, generalized forms into over 20 distinct orders encompassing virtually every conceivable ecological role. Some lineages pursued aquatic lifestyles, with early whales like Pakicetus beginning the remarkable transition from land to sea around 50 million years ago. Others took to the skies, with the first bats appearing in the Eocene and achieving powered flight through entirely different anatomical innovations than their ancient pterosaur predecessors. The most dramatic transformations occurred on land, where mammals experimented with size, diet, and lifestyle in ways that would have been impossible while dinosaurs dominated terrestrial ecosystems. By the early Eocene, just 10 million years after the extinction, Some mammals had already achieved massive size. Coryphodon reached the dimensions of a large rhinoceros, while the bizarre Uintatheres developed elaborate skull protuberances and saber-like canine teeth that rivaled those of any predatory dinosaur. Yet it was during the Paleocene-Eocene thermal maximum 56 million years ago that mammalian evolution reached a crucial turning point. This dramatic warming event, triggered by massive carbon release that raised global temperatures by 5 to 8 degrees Celsius, created greenhouse conditions more extreme than any since the Mesozoic. Palm trees grew at the Arctic Circle, while crocodiles basked in polar regions that would later be entombed in ice. These tropical conditions enabled mammalian dispersal across land bridges that connected previously isolated continents. North American mammals migrated to Europe across the Greenland-Scotland Bridge, while Asian forms colonized North America via the Bering Land connection. This intercontinental mixing accelerated evolutionary innovation as different mammalian lineages competed and hybridized in novel environments. The early primates made their first appearance during this warm interval, with creatures like Plesiodapus developing the grasping hands and forward-facing eyes that would characterize the order. These early primates were not yet the large-brained, highly social creatures that would eventually give rise to humans, but they possessed crucial adaptations for arboreal life that positioned them to exploit the extensive forests of the greenhouse world. As the Eocene progressed, mammalian diversity reached levels that would not be seen again until the modern era. The archaic mammalian orders that had dominated the Paleocene began giving way to more modern forms, including the earliest representatives of groups familiar today. The first true carnivores evolved sophisticated meat-shearing teeth, while early artiodactyls, the group that includes pigs, deer, and cattle, developed the specialized digestive systems that would enable them to exploit plant resources more efficiently than their predecessors. The cooling that began around 34 million years ago marked another crucial transition in mammalian evolution. As greenhouse conditions gave way to a more temperate climate, the Antarctic ice sheet began forming for the first time in over 100 million years. This global cooling event, triggered by the opening of Drake Passage between Antarctica and South America, fundamentally altered ocean circulation patterns and ushered in the icehouse world that would characterize the remainder of the Cenozoic. The climate shift had profound effects on mammalian communities worldwide. Many of the archaic forms that had flourished in greenhouse conditions went extinct, while more modern lineages adapted to cooler, more seasonal environments. Grasses, which had first appeared during the Cretaceous but remained relatively minor components of ecosystems, began their rise to dominance as cooling and drying created conditions favorable for grassland expansion. The Miocene epoch, spanning from 23 to 5.3 million years ago, witnessed the transformation of Earth's terrestrial ecosystems through what scientists call the grassland revolution. Vast prairies and savannas replaced the forests that had dominated earlier periods, fundamentally altering the evolutionary pressures facing mammalian herbivores. The high-fiber diet provided by grasses required new digestive strategies and dental adaptations, driving the evolution of the grazing specialists that dominate modern ecosystems. This grassland expansion had cascading effects throughout mammalian communities. Predators evolved new hunting strategies to pursue prey across open landscapes, while herbivores developed enhanced sensory systems and social behaviors to detect and escape from predators in environments with limited cover. The famous Red Queen arms race between predators and prey reached new levels of sophistication as both sides evolved increasingly advanced weaponry and countermeasures. Among the most significant Miocene developments was the radiation of hominids in Africa around 7 to 8 million years ago. The cooling and drying that created grassland environments also fragmented the African forests where early primates had evolved, creating a mosaic landscape of woodland and savanna that favored upright locomotion and tool use. The human lineage diverged from that of our closest living relatives, the chimpanzees, sometime between 6 to 9 million years ago in response to these changing environmental conditions. The Pliocene and Pleistocene epochs, beginning around 5.3 million years ago, saw the intensification of glacial-interglacial cycles that would define the most recent phase of Earth's climate history. The growth of major ice sheets in the northern hemisphere around 2.6 million years ago ushered in the Quaternary ice ages, a period of dramatic climate oscillations driven by orbital cycles that would profoundly influence human evolution. These ice ages operated like a vast evolutionary laboratory, repeatedly isolating and reconnecting populations as glaciers advanced and retreated. The environmental pressures created by fluctuating climate drove rapid evolutionary change in many mammalian lineages, but perhaps none more dramatically than in the human ancestral line. The genus Homo appeared around 2.8 million years ago, coinciding with intensification of glacial cycles, while our own species emerged around 300,000 years ago during one of the most unstable climatic periods in Earth's history. By the time modern humans began their global expansion around 60,000 years ago, the mammalian radiation had populated virtually every terrestrial environment on Earth. From tiny shrews weighing less than a coin to massive proboscideans exceeding the size of any land animal since the dinosaurs, mammals had achieved a diversity and ecological dominance that surpassed even their reptilian predecessors. Yet the arrival of human consciousness would prove to be as transformative as any asteroid impact. For the first time in Earth's history, a single species had evolved the capacity to understand its own evolutionary origins and to consciously direct the future trajectory of life itself. The Age of Awareness had begun.